Part 2 video. This, okay, I'm having a little bit of issues with my recording. I guess I forgot to delete some stuff. So I'm going to have to, it's probably going to have like several parts. But anyway, back to this. We're going to do 1, 2, and 3 after I go over, haven't done any math. I was in the middle of going over these examples of these notes. An object in circular motion, it talked about what is the agent applying the force. So if a ball is attached to a string, it says, and say you're spinning around like a slingshot around in a circle above your head, okay? Well, it says, first of all, what agent is applying the force? It would be the force is applied by the string. The string is actually applying the force to the ball. If that string were cut, the ball would go in a straight line. It would follow Newton, okay? B, a dog runs around a circular track at a constant speed. A dog running around a circular track. What is keeping that dog in a circle? Think about it. It's actually the friction between the dog's paws and the ground. So like the track and his paws have to have friction. One way to prove that is he would not be able to be in a circular track. Say you took a little baby chihuahua and you had him running around in a circle. Say you trained him, well, not baby chihuahua, but like maybe he's like, 5, 6 months old. You taught him to run around in a circle. You're real happy. Then you take him out to like the hallway at school, like a hard tile floor. But say you oil down the floor. Now you tell the little chihuahua to run her in a circle, or tell him he's not going to be able to do it. There's no friction. His legs will be doing like this. He might be moving ahead like slowly like this, but he's not going to be able to turn. I'm being goofy. But you know what I mean. The same way driving a car, if you drive into oil or in a bicycle, oh boy, I did something like that on a bicycle recently. You go into like an oily area, and boy, suddenly you can't even, you can't even go straight. You have no direction anymore. Okay. So to stay in a circle, you need friction between the wheel and the ground, or in this case, the dog's feet and the ground. A roller coaster moves in a constant loop in a vertical upside down loop. Now that's interesting. Why could a roller coaster, think about that. We'll talk about that more. How can it go on a little car? A little car can go upside down and it stays in a circle. It doesn't fall or anything. Well, the reason it has to do with it's going so fast, and it's the track. The track is keeping it in a circular motion. It collides with the track, and the track is always pushing it back towards the center every moment as it goes around. The moon orbits the Earth at a constant speed. That I already told you a moment ago. It's the gravity of the Earth. So like as the moon goes around the Earth, it stays in a circle because the Earth's gravity on the moon is just like a rope. Well, I didn't do too good a job of that. It's better with a little ball and a string. I have that at school somewhere. I think I do have one. I'll try to find one at some point here to show you. Okay. All right. Now, uniform circular motion is what I just told you. When an object is moving in a circle and those three conditions are met. Obviously same speed, constant speed, but yet the direction changes. The radius would be constant. And you don't have to worry about this other part here. This is a derivation now, getting into more complex math, about how they're going to form some equations. But if you wanted to read over it and study it, you could. But you don't have to read all these notes in this stuff. You can glance over it, and there's a little derivation there. Like, what in the world? That's more like something from AP Physics. And I don't even teach AP Physics, okay? But it would show you how you derive the equations that come up in Section 70-B. And these are the equations for uniform circular motion that we're going to be using. And I'm probably going to have to pause it and continue this. But anyway, I'll write them down here. 70-B. One of them, okay, velocity. You're not even going to see that one, so I'm not going to take it away. Change in the radians or radius over change in time. Here's one you've seen. If an object is moving in circular motion all around, the path that's going on, how can I calculate if I wanted to know how big is that circle? If I drew that circle all around, how big is that circle? Well, circumference is 2 pi r. You just need to know the radius. If I know the radius, how far it is from the center to the end, that will tell me the pathway, the perimeter, or the perimeter of a circle is called circumference, the circumference. Okay? Here's one interesting. Velocity, and this kind of makes sense. Oh, I got to explain this a little bit. Well, I'll say it now. 2 pi r over capital T. Now, a lowercase t is time. Capital T means period. Now, a period is means the amount of time it takes to make one entire circle. Okay? So, I'll give you an example. The Earth travels around the sun. What is the period of the Earth going around the sun? The period is 1 year. Or it takes 365 days for the Earth to go one time around the sun and get back to the same place where it is today. 1 year from the day, it will be right back exactly where it is on its circle, on its elliptical orbit. But anyway, it will be right there. That the period would be 365 days. Okay. Now, if you could turn that into how many, you could turn that into miles per hour or whatever as well. But how the circumference and how much time? You could put it in seconds. In fact, it's supposed to be in seconds. The period in seconds. So it's going to happen later on when we get to doing, pretty soon, we're going to be doing planetary motion problems in this chapter. And anytime you write, oh, okay, the period of the Earth is 365 days, 1 year. No, you got to convert it into seconds to put it in the equation. So that'll be the period, the time in seconds it takes to make one loop. That's the period. Period in seconds, time to make one loop or orbit if we're talking about planetary. So what I'm teaching you right now is true for planetary motion, but it's also true for just any circular motion. And right now we're just kind of talking about